text. There are agreements so fundamental that we never think to question them. We wake up, glance at a clock, and the number we see is the same number displayed on a clock in Tokyo, in São Paulo, in Cairo. Not just the hour, adjusted for time zones, but the actual tick, the actual rate at which time is counted. 1 second here is 1 second there. 1 second today is 1 second as it was measured 50 years ago. This seems obvious. It seems like it could not be otherwise. But it was not always this way. And the story of how humanity agreed on what a second actually is, not just what to call it, but what it physically means, how to measure it, and who gets to decide, turns out to be one of the stranger and more consequential negotiations in the history of science. It is not simply a story about clocks. It is a story about the nature of physical reality, about who controls the invisible infrastructure of modern civilization, and about what happens when the thing you thought was fixed turns out to be slowly drifting. To understand what was at stake, you need to go back to how the second was originally defined, and how casual that definition actually was. For most of recorded history, a second was simply 1/86,400th of a day, the day being divided into 24 hours, each hour into 60 minutes, each minute into 60 seconds. This definition had the advantage of being intuitive. The day was something everyone experienced. The second was just a very small slice of it. The problem was that the day is not constant. The Earth's rotation is not perfectly uniform. It slows down, speeds up slightly, wobbles under the gravitational influence of the moon, the sun, the redistribution of mass as glaciers melt and tectonic plates shift. A day measured in 1900 was not exactly the same length as a day measured in 1950. The difference was tiny. We are talking about fractions of a millisecond. But for astronomers, navigators, and eventually engineers building systems that depended on precise timing, fractions of a millisecond mattered. The first serious attempt to fix this problem came in 1956, when the international scientific community agreed to redefine the second not in terms of the Earth's rotation, but in terms of the Earth's orbit around the Sun. The tropical year, the time it takes for the Earth to complete one full orbit, was more stable than the day, and so the second was redefined as a specific fraction of the tropical year, as measured in 1900. This was called the ephemeris second. It was more precise than the old definition, and it solved some problems, but it introduced new ones. To measure the ephemeris second accurately required observing the position of celestial bodies over months and then doing complex calculations. You could not, in any practical sense, go into a laboratory and measure a second in real time. The definition was precise in principle, but deeply inconvenient in practice. What changed everything was the discovery that atoms could keep time. Not atoms in general, but atoms of specific elements, when exposed to precisely calibrated electromagnetic radiation, will oscillate between two energy states at a rate that is extraordinarily stable and crucially identical for every atom of that element anywhere in the universe. An atom of cesium-133 does not care where it is. It does not care about the season. It does not care about the gravitational tug of the moon. It oscillates at the same rate in a laboratory in Paris as it does in a laboratory in Boulder, Colorado. This property made it possible to imagine a clock whose rate was not tied to any astronomical observation, but to something far more fundamental, the quantum behavior of matter itself. In 1967, the General Conference on Weights and Measures, the international body that governs measurement standards, made a decision that redefined physical reality as we measure it. They declared that 1 second is the duration of exactly 9,192,631,770 oscillations of the radiation corresponding to the transition between two specific energy levels of the cesium-133 atom in its ground state. This sentence is worth reading slowly because hidden inside its technical density is something genuinely remarkable. The second, the unit on which clocks, computers, telecommunications, navigation systems, and financial networks all depend, was no longer defined by the movement of the Earth. It was defined by the behavior of an atom. The universe, in a sense, had replaced the sky. The number 9,192,631,770 was not chosen at random. It was chosen specifically to match, as closely as possible, the length of the ephemeris second that had come before. The scientists did not want to introduce a discontinuity. They wanted the new definition to be more stable, more precise, and more practically realizable than the old one, while producing results that were indistinguishable from what had been measured before. This is a recurring feature of how measurement standards evolve. The goal is almost always to improve precision while preserving continuity. A new definition that produced different numbers would create chaos in every field that depended on the old numbers. The art is in making the transition invisible, but the transition to atomic time created a problem that nobody had fully anticipated. The atomic second was now fixed, the astronomical day was not, and over time the two drifted apart. As the Earth's rotation gradually slowed, by amounts too small to feel but not too small to measure, the atomic clock ran very slightly ahead of where the Sun would predict it should be. By the 1970s, this accumulated difference had become large enough that practical timekeeping systems were beginning to show a real gap between atomic time and solar time. If left uncorrected, the drift would eventually mean that noon, by atomic time, would occur when the Sun was not actually close to its highest point. This would take centuries to become noticeable to ordinary people, but it would affect navigation systems, astronomical observations, and anything else that needed to relate clock time to the real position of the Earth. The solution adopted in 1972 was the leap second. Whenever the gap between atomic time and solar time approached 1 full second, the timekeepers at the International Earth Rotation and Reference Systems Service would announce, usually several months in advance, that a specific minute at the end of a specific day would contain 61 seconds instead of 60. The atomic clocks would pause, in effect, and let the Earth catch up. This happened 27 times between 1972 and the early 21st century. It seemed like a reasonable compromise between the perfection of atomic time and the reality of astronomical time. What nobody fully appreciated in 1972 was how important precise, continuous timekeeping would become to digital infrastructure. The Internet, satellite navigation, financial transaction systems, telecommunications networks, power grid synchronization, all of these depend on clocks that agree with each other to extraordinarily fine tolerances. A leap second is not just a footnote in an almanac, it is an event that every networked system in the world needs to handle correctly, simultaneously, without failing. And handling it correctly turned out to be significantly harder than it seemed. In 2012, a leap second inserted on June 30th caused serious problems for a significant number of Internet servers running the Linux operating system. The way these servers handled the extra second triggered a software bug that caused them to lock up or slow to a crawl. Reddit, LinkedIn, Foursquare, and various other major websites experienced outages or severe performance degradation for several hours. Engineers around the world scrambled to patch systems they had not realized were vulnerable. This was not a catastrophic failure of the global Internet, but it was a clear demonstration that the gap between the physical reality of an imperfect rotating planet and the mathematical cleanliness expected by digital systems had become a genuine engineering problem, not just an abstract concern for metrologists. The debate about what to do with the leap second went on for decades inside the international measurement community. One side argued that civil time, the time on public clocks, in legal systems, in the everyday world, had always been tied to the position of the sun, and that severing this connection would be a philosophical error with consequences that accumulated slowly and were therefore easy to underestimate. The other side argued that the increasing cost of leap seconds to digital infrastructure was real and growing, that the gap between atomic and solar time could be allowed to accumulate for centuries before it became perceptible to anyone without a telescope, and that the practical benefits of a continuous, uninterrupted atomic timescale outweighed the abstract importance of keeping clocks synchronized with the sun. In 2022, after years of negotiation, the General Conference on Weights and Measures voted to suspend leap seconds indefinitely starting in 2035. After that date, atomic time and solar time will be allowed to drift apart without correction until at least the year 2135, at which point the accumulated difference will be large enough that some new mechanism, perhaps a leap minute, may be needed. This decision was not unanimous, and the debate continues among the people who think about these things professionally, but it reflects a clear judgment about where the weight of practical need now lies. The needs of digital infrastructure, of the systems that now run much of the world's commerce, communication, and navigation, have become more important than the symbolic connection between the clock and the sky. What does any of this have to do with ordinary life? More than it might appear. Every time you use GPS to navigate, the system depends on atomic clocks aboard satellites staying synchronized with each other and with receivers on the ground to within nanoseconds. A nanosecond of error translates to about 30 centimeters of positional uncertainty. The precision of atomic timekeeping is not an abstraction. It is the reason your phone can tell you which side of the street you are on. Every financial transaction that occurs electronically is time-stamped with atomic precision, because the legal validity of transactions in many systems depends on the sequence being provable, and the sequence can only be proven if the timestamps are reliable. The infrastructure of modern life is, in a very literal sense, built on the stability of a unit of time defined by the quantum behavior of an atom. There is a deeper point worth sitting with. The second, as currently defined, is stable to a degree that is almost impossible to intuitively grasp. The best atomic clocks in the world, optical lattice clocks, which use different atoms and different transitions than the cesium standard, are accurate to within 1 second in 30 billion years. The universe is approximately 13.8 billion years old. These clocks would not have lost or gained a second since before the Big Bang. This level of precision is not needed for navigation or finance, but it matters for science, for testing theories of gravity, for detecting gravitational waves, for probing whether fundamental constants are actually constant or whether they drift over cosmological timescales. The most precise clocks in existence are simultaneously practical infrastructure and instruments for investigating the deepest questions about the nature of physical reality. And yet this extraordinary stability was achieved through a series of decisions made by committees, by scientists and diplomats and engineers arguing in conference rooms in Paris and Geneva and Boulder about numbers, definitions, and practicalities. There is something worth noticing about that. The most fundamental facts about how we measure reality are not discovered and then simply applied. They are negotiated, they are agreed upon, they reflect the state of knowledge, the state of technology, and the distribution of influence at the time the agreement was made. The cesium-133 second is not the only possible way to define a second. It is the way that was chosen at a particular moment by people who had particular reasons for choosing it. Future decisions about whether to move to an optical clock standard, about how to handle the growing divergence of atomic and solar time, will also be made by people, in committees, with all the complexity that implies. The invisible infrastructure of time is maintained by a small number of institutions and a relatively small number of people. The International Bureau of Weights and Measures, based in a park outside Paris, coordinates the world's timekeeping. National Metrology Institutes, in Germany, France, the United States, Japan, China, the United Kingdom, and a handful of other countries, operate the atomic clocks whose combined output defines coordinated universal time, the time scale used by the global internet, by satellite navigation, by financial systems, by everything that depends on synchronized clocks. These institutions are not famous. The scientists who work in them are not famous. But if their work stopped, the effects would ripple through every networked system on the planet within days. This is characteristic of the most important infrastructure. It works so well, so continuously, so invisibly, that it creates the illusion of being natural, of being simply the way things are, rather than the way things were carefully arranged to be. The second that ticks on your phone right now is the result of international treaties, decades of experimental physics, engineering solutions to problems that barely existed when the treaties were signed, and ongoing human effort to maintain a system whose complexity is far beyond what any individual can fully grasp. This is not a reason for anxiety. It is a reason for a particular kind of attention, the attention that asks, about the things we take most for granted, how did this come to be? Who decided? Who maintains it? And what would it take for it to change? The next time you glance at a clock, consider what that number represents, not just the time of day, adjusted for your location and season, but the output of an agreement, a physical, philosophical, and diplomatic agreement about what the most fundamental unit of time actually means. An agreement reached by people who knew they were doing something important, who disagreed about how to do it, who made compromises, who sometimes got things wrong and went back and fixed them, and who built something that has lasted and that every person on Earth now depends on without knowing it. That is, when you look at it clearly, a fairly remarkable thing for a collection of committees to have done. Have you ever noticed a moment when precision timing became unexpectedly important in your own life? A flight missed because of a synchronization error, a transaction that failed at the boundary of a second, or simply the first time you understood how GPS actually works? Share in the comments. These small personal encounters with the infrastructure of time are often where the abstract becomes suddenly, concretely real. And if this shifted something in how you see something as ordinary as a clock face, that is the point. Understanding what holds the ordinary world together changes your relationship to it, not with anxiety, but with something closer to informed appreciation. Remember this: the second is not a fact of nature. It is a choice, a precise, carefully reasoned, internationally agreed-upon choice that the universe happens to accommodate. The difference between those two things is everything.